Let's start with a short story. So let's imagine that we just shipped our first AI agent to production and the clients or users start complaining. So now the question is, what do we know? What do we do? How can we get into the system and really understand what's going wrong? And how can we understand why the users are complaining, right? Because our goal is to be able to get into the system and really understand why that for a specific input do we get the wrong output. So we should be able to answer questions such as, how can we look at the client's prompts and answers and make the connections between good inputs and outputs and good inputs in the end, because any input should be supported, right, in our system, and bad answers. But also we want to dig deeper into the system, right? So we should be able to answer questions such as, what's the client's input context, right? Which is already harder to understand. We want to understand that for a specific input, our agent retrieve a specific context and understand and debug if that context is actually relevant to the input or if is there something wrong to it. And we should also move a step forward and be able to answer questions such as, how can we measure the impact of a new feature? Because most probably after we first ship the first version of our agent to production, we either need to fix bugs, most probably the system is not perfect and we have to fix bugs, or ship new features, right? And the reality is that when we make a change to a part of the agent, such as tweaking a prompt, there are big chances that you will mess up other parts of the system and other features that you thought are working, but you now will break them. So that's why we should measure each change and see that whenever we change something to a prompt, to a tool, to a context or whatever, we keep the system as it should be plus the fix or new feature, or we break something along the way. So that's what observability is all about, right? So, hey there, I'm Iusztin, a senior AI engineer with 8 years of experience in the field and the founder of Decoding ML, where we push content on production AI, such as newsletter, articles, open source courses, and so on and so forth. So today's presentation is called LLM and RAG Evaluation Playbook for Production Apps. So as this is a webinar, I want in the beginning to start with a really quick presentation where I set up the context of the code and what you need to understand at a higher level overview. Here, I won't go deep into the details, and we will do that while we open up the code and start implementing a evaluation solution. So let's start the presentation with the basic architecture of a RAG agent. And I want here to understand the core components of a RAG agent, which are crucial to understand on what and where can we monitor and evaluate the system, right? So the first one, any RAG system has two main aspects: the ingestion part, where you populate your vector database, your memory, your database, or however you want to call it, and the inference part, where you actually have the agent that does its things, right? But if we go deeper into the system, I think we can decompose it in 5 core elements. Which the first one is the RAG feature pipeline, which, as I said earlier, its scope is to take some data sources, some raw data sources, and transform them into a way you can ingest them into your memory, which is usually a vector DB, but it can be a document database, a graph database, or whatever makes sense for your application. So here at this step, we usually process these data sources, we clean them if necessary, we chunk them, we embed them, we pre-compute some metadata along each chunk and embedding, and load everything into the memory. So the memory is actually the second part of the system, where we usually have the short and long-term memory. It makes sense to also save the short-term memory, right? Because like this, we can handle multiple users and sessions and all of that. And next, we move into the inference world, where we have the agentic RAG inference pipeline, how I like to call it, which is where we actually do all those agentic things with we hook an LLM to some tools, to some long context, where we do the retrieval specific to an input, right? We do MCP calls or whatever. So here is where all the agentic logic comes. And the next element is usually an LLM API, right? So we need an LLM to do all this agentic stuff, which is usually done through an LLM API, such as the one provided by OpenAI, Anthropic, or even something open source hosted on your on-premise system. But this doesn't necessarily have to be an API. You can also like host something directly locally with a Llama or whatever. The idea is that you have an LLM that you need to consider and be good enough for your system. And the final piece of the puzzle is the observability pipeline, which usually takes prompts and trace spans and all of that and monitors them and evaluates them and so on and so forth. So here we just had an overview of a classic RAG agentic architecture. So now the quick question related to this webinar is, where can we evaluate it, right? So actually, I suggest that we can evaluate it in 4 key zones, right? So the first one is related to how you preprocess your data and load it into your memory. So here we should consider how we chunk the data, how and what do we add to the metadata, how do we compute the embeddings. So all of these elements will have an impact on how you retrieve the data and how the context is added to your system, right? Next, we should really care about the retrieval step, because actually adding a RAG component to your system, to your LLM system, adds a lot of complexity. As you can see, adds these 2 elements that we need to take care of. So here we should really consider on evaluating the retrieval phase. So we should answer questions such as, are the elements relevant to the input query, right? Are the elements enough to answer the input query? And so on and so forth. The next phase is we should also isolate the LLM, either if it's, again, an API or something hosted by you or something fine-tuned by you. It doesn't matter. We should isolate the API and evaluate it and understand if it's good enough for our specific use case. And the 4th element is where we want to actually evaluate the agentic RAG app as a whole. And here we usually use LLM as judges to do and to compute all kinds of metrics related to your input, output, and context. And we kind of treat the system as a black box, but I say kinda because we usually need the context that's used by the agents to compute the outputs to actually have some relevant metrics. So now let's dig a little deeper into all those elements. So as I said, we start with the RAG feature pipeline, where we want to evaluate things such as the extracting logic, where a very common scenario is to extract PDFs and do some OCR on top of them. But this is just an example. The idea is that usually here we apply all kinds of algorithms, which we will want to isolate and evaluate. Also, the chunks, like the size and the context, are super important. And you could evaluate your system based on different sizes of chunks, for example, and see how different sizes impact your system. Also, the embedding model per se, of course, is super important, and we should isolate it and evaluate it. But these can all get super tricky really fast. And that's why I think that a really quick way of evaluating your RAG ingestion pipeline, your RAG feature pipeline, is to visualize your embeddings, right? And we will do that in this webinar. Next, how we evaluate the retrieval per se. So here, I think that we have 2 main ways of doing it. But what I want to highlight is that we have 4 moving components during your retrieval. So you have usually your query, your answer, and the retrieve context, and the ground truth context, right? So depending if you have your ground truth context or not, you can do more or less with the metrics, because in reality, most often you don't have any ground truth context, so things get trickier. So based on these 4 elements, you can compute things such as context recall and precision metrics using LLM as judges, which we will do in this webinar. And if you have ground truth context and care about the ranking of your retrieved chunks, you can also compute all kinds of ranking metrics that are usually used in recommender systems. But this is more trickier because we need ground truth context, so we want to do this in this webinar. And the last phase is how can we actually evaluate the agentic app. So here I see this in like 3 phases, and it's not really evaluation, but it's more observability, in the sense that we want to do monitoring plus evaluation. And I think monitoring is key to really understanding and evaluating with a human on what's going on, because computing metrics is tricky. So actually going yourself into the system and understanding and looking at everything step by step is super important. So we can do things such as monitoring traces and actually prompt versioning. And this is on the monitoring side. And on the evaluation side, we usually use LLM as judges, either offline, right, when you implement specific features, and online, which is done during production. And we compute metrics such as hallucination, moderation, answer relevance, and so on and so forth. And the last step is usually user feedback, which can again be done internally, right, by your engineering team, product manager, or whatever users are using internally your product, which is what we will show you how to do in this webinar. And the ideal phase is to collect user feedback from your actual users. But this is trickier because we don't have a product here, right? So yeah, this was the quick presentation. And the last thing I want to highlight is some tools which are often used for evaluating. So system basic, more exactly, some tools used for LLM ops, more exactly observability part of LLM ops. So on the open source spectrum, we have Opic, which we will use in this webinar, but I also suggest looking at Langfuse and Phoenix, and some closed source tools. Some popular ones are Langsmith, Galileo, and Human Loop. So yeah, this was the end of the presentation. And if you're curious for more, you can follow up on the Field Agents course, which was, this webinar was inspired from this course. The good thing is that it's free, it's open source, it has 6 modules written and video, and yeah, no hidden cost. You can just check it out on GitHub with this link from here and start implementing. And you can also subscribe to Decoding ML and LinkedIn for more similar content. So now let's move on to the code and yeah, start implementing this an evaluation and observability layer on top of a RAG agent. So let's start the webinar by walking you around the workshops GitHub repository, which is linked in the abstract of the webinar. So here we have multiple workshops, but we are interested just in this one called Convergence 2025. So we can just click on this link. So here we have the following structure. So we have the solution and the template folders. The solution one, it's a standalone Python project which has everything already implemented, and we can use it as a guideline in case we get stuck or don't want to write the code yourself. And the template is based on the solution, but we just remove parts of the code which makes sense to observability, so we can just focus on these ones and implement just what we care about. Because remember that evaluation usually sits on top of a working system, and monitoring itself, usually observability, sits on top of a working system. So here we actually implemented a agentic RAG, a simple application we use to showcase our ideas, right? So that's what we can already find implemented, and we'll focus just on the evaluation and monitoring parts of the workflow. So now let's open the template folder. Here, as you can see, you have everything you need to set up the code. Basically, you have the prerequisites, the cloud services such as Opic and OpenAI. You need to get the API keys for both. The thing is that Opic is open source, but we use their self-hosted platform to make things easier. And for the Open API is pay-per-use, but it will just take a few cents to run all of this. And then we can just start copying all these commands, and which will help us set up the code base. So we git clone the repository. We then move to this specific folder because, as I said before, also the solution and the template folder are standalone Python projects, so they make sense on their own. And then we can just open this template folder with the ID of our choice. We will use cursor, but to be honest, anything will work in this use case. So use whatever makes sense for you. And then we use UV to install all the Python dependencies. UV is like the latest kid in the block in the Python project management system tools. It's written in Rust. It's like blazing fast. Just let's see. And then boom, it's everything is installed, right? So we have like 15 dependencies, and they were installed in a few milliseconds, which is great. So usually I switch from Poetry to UV, and I will never go back, to be honest. And it's also easier to be used, and yeah, I just like it. And then yeah, let's start using the README from the repository to avoid switching back and forth between the browser and the IDE. And the last step is just to check that we use the right Python version, which is described here in Python version. So we usually use these files to be sure that we use the right Python configuration. Next, we have to fill in the .env file, which will load the API keys. You can just use this .env.example as an example and fill in these two environment variables with your API keys. So I will actually, to avoid showing you my keys, I will just copy it from my existing project. So yeah, just give me a second to do that. Okay. Right, so now I have this file here. I won't open it, but it has the right API keys to run this project. As the project structure is like a standard modern Python project structure, which doesn't use notebooks. So we won't use notebooks, just plain Python scripts, because we want to go to production here, not to experiment things. And as infrastructure, we actually use Quadrant as our vector database. So we hooked up it to Docker so we can easily run it locally. So we just need to run this quick command, which will open it in Docker. So as you can see here, now we have this Quadrant latest container running on this port. So just make sure that this port is not used by any other Docker container or what other application, because this won't work in that use case, right? So now basically we have set up the local Quadrant, which we will use in our use case. Okay, so now for the code itself, let me quickly explain what this agentic RAG is doing, right? So this webinar is inspired by my latest Philo Agents course, which is, as a use case, we managed to impersonate different philosophers, hence the Philo Agents name. Basically, through prompt engineering and RAG, we managed to impersonate philosophers such as Socrates, Plato, Aristotle, Turing, and so on and so forth. So we will use this code as a base to have some agentic RAG system working, and we will implement the observability part on top of it, right? So to do that, first, we actually need to create the long-term memory, which basically here at this step, let me just run it. So we use make to encapsulate our commands, so we make running everything easier. But as you can see, we use UV to run this part, to run various scripts. Under the tools folder, we actually have all the scripts we will use in this project. So now we call the create long-term memory one, but we also have like the call agent one, which calls the particular agent for a specific philosopher ID, like Plato, Aristotle, Turing, and so on and so forth, and with a specific query. As you can see now, with the create long-term memory, at the create long-term memory step, we scrape various sites such as Wikipedia or similar ones to get context on those philosophers. So when we actually talk to them, we'll use agentic RAG to get insights about their life, about their work, and so on and so forth. So we actually anchor the answers in real facts. So this is what we want to observe, to evaluate, monitor if the agents actually use this memory to answer you correctly, or how they use it, right? Okay, so now the memory is created. Let me quickly open a browser, and you can actually go to the Quadrant dashboard, which is hosted on HTTP localhost. So here's where it is hosted, right? So here we can see that everything loaded correctly. Just type in your browser and you should find this collection, philosopher long-term memory, with around 1000 points. Okay, so if you click on it, you can play around with the collection, and we will, but a little bit later. Okay, so just to make sure that the system is working correctly, just let me call the agent once, right? So let's ask Plato, when and where were you born? And also tell me about your life, work, and beliefs, right? So he gave us this: I was born around 428 BC in Athens, and so on and so forth. So when we see this, we are not actually sure that, okay, it hallucinated. Is the answer anchored in the long-term memory, which we know it's correct, and so on and so forth. So our goal is to answer these questions and actually to also see that, is this answer comprehensive enough, right? So do we have all the details that we want related to the question here? I don't know. Is there any toxicity in there? And so forth. And also we want to make these queries more complicated as we go, because the beauty of agentic RAG is that if in the query you have multiple questions under one single query, it should query the vector database multiple times and actually isolate each question and query the vector database per isolated question. And we want to see if it will actually do that. Okay, and yeah, so I think we are good enough in the setup, and let's start actually implementing the monitoring part. So here, as you can see in those notes, I tried to guide you in what you actually need to implement. And also, we added to-dos. I added to-dos based on each module where you should implement what, right? So we have basically 4 modules, module 1, module 2, module 2 and 3, because these are they kind of overlap with each other, and module 4 as reflected in the abstract, and then we will implement them sequentially. And yeah, let's start with module 1, where basically you have to add prompt monitoring. Okay. Okay, so to do that, we will go to this to do. Okay, so basically we need to go here and here and here. Okay, so actually what this is, so actually to better understand and not go like isolated like this, let me quickly walk you over the source, the structure of the repository, right? So as you can see, you have the evaluation playbook, a Python project where we have those 4 folders. The domain folder contains like pydantic modules such as the prompts, all kind of philosophically related entities, and so on and so forth. We don't have to care a lot about this folder, to be honest. In the evaluation is where we will play the most and implement the evaluation logic. RAG, again, we have all kind of RAG logic here. As this is not a RAG webinar, we will not go into these folders, but as you know, here you have everything related to ingestion and retrieval. And in the workflow folder, we actually have the LangGraph elements, right? So the graph, the nodes, and all of that. Again, this is not a LangGraph webinar, so I won't go into all of this. And we have the config where we load all the settings with using pydantic settings, the quadrant wrapper talk to quadrant, and the OPIC utils. So here we actually configure OPIC to make it workable into our system. Here we have nothing sexy to show, so that's why I just pre-configure it. So before starting the implementation, the last step is to select the interpreter to avoid having these ugly red lines. Okay, so now let's just start searching our to-dos and start configuring this bad boy. Okay, so as I said, in that configure function, we configure OPIC, where we basically specify the API key, the project key, the workspace name, and so on and so forth. It's just configuration, so I won't go too deep into this part. But the next step is to actually hook OPIC into our LangGraph agentic RAG system. So they're really well integrated with LangGraph, so we don't have to do much here, right? So all that we have to do is just put this OPIC tracer, which will basically listen to your whole graph and just capture everything. I will run it soon. Actually, let's just run the question that we ran before. Let's run it now with this OPIC configuration. But lastly, oh yeah, so we have two kinds of graphs here. We have a simple call async implementation of LangGraph, and you also have a streaming implementation of LangGraph where we stream token by token everything as you've seen here. So that's why we build the graph using the same create workload graph function, right? But how we call it differs. So that's why we need to put 2 configurations on each. Yeah, let's now run this, and I will show you afterwards how to look at this into OPIC. So as you can see, we use the stream function over here, and that's why we have seen everything step by step. And now we can see that everything is logged into OPIC. We can see how the prompts are monitored inside OPIC by clicking on this link, which will open the OPIC dashboard. You probably have to log in. First you have to log in, and then you will be sent to this view. So you go to projects, and you have to go to this convergence 2025 project. And here I like to order this by time, so we can actually see the latest call that we did in the CLI. So we open it, And we can see now the whole prompt trace, right? So at the beginning, we can see the initial input and output. So we can actually see the input question, which was this one, when and where were you born, blah, blah, blah. And along some other context and metadata injected automatically by the code. So basically, this is the actual message that we send to the LLM, to OpenAI in this use case. And we can also see some metadata like the thread ID and so on and so forth. And if we start, and we can start digging deeper into what happens under the agent, like behind the scenes, right? So we have the LangGraph itself, and then we have this conversation node, which actually gets this input and outputs the next step. So basically, the conversation node is like the agent, right, which decides based on specific inputs what to do next. So in this particular use case, we can see that it indeed decided to call this tool, Retrieval Philosopher Context, with the query Plato, and that's it. So also here, we can see the actual call that was done to OpenAI to decide to get this output. We can see how long it took to run, the number of tokens, the cost of generating this output, and so on and so forth. And here we can actually see the tool call, which is basically our retrieval step. And here we can see based on the specific input, what kind of output we got. So basically, indeed, we retrieved the necessary information to answer questions such as when and where it was born, and so on and so forth. And afterwards, it took this, we can see that it took this content. So we can slowly see how the context of the agent is built up and how the final output that we saw in the ID was answered, right? So yeah, we get a lot of insights digging into this tool. So I don't want to waste the whole webinar like going to step by step, but the thing that you have to understand here is that usual logging doesn't work really well with monitoring prompt traces, because as you can see, a single call to an agent is very complex. So using basic logging tools won't get you that far, right? So that's why we need these specialized tools to really nicely see each call and to dig into each. Now, the thing is that because we used LangGraph specifically, it is enough to do this OP tracer, and it knows to pick up on each like node call and edge and LLM call and all of that. But you can get more granular into how you decide to monitor each step. But usually you do that through a Python decorator or other like similar configs, which is really easy. So I won't go into that. But what you need to understand is you want to get to this state where you can see each state of the agent call. And also you can see like how long it takes to run each step, so you can quickly detect bottlenecks into your system, or how many tokens you have for input and outputs, or so you can quickly see what specific LLM call is very, I don't know, token heavy, and also the cost and so on and so forth. So this is like a really quick win to understand what happens behind the scenes, right? Okay, so we'll go back and forth to this view, but this is the first step that I really wanted to show you. Okay, so let's go back to our README, because this will be like our guideline. And the next step is to evaluate the retrieval, right? So now we have this basic monitoring, which kind of works mostly on the inference RAG agent side, so we can see what happens. So this is like the quick win that you want to implement first, usually. Now let's move to a more structured approach, where we take everything step by step, and we want to evaluate everything step by step relative to the diagram I showed you in the beginning. So the first one is to look at the quality of the embeddings, right? So this is like a very strong signal on how your embedding space looks like, and if you need to further improve your algorithms, your extraction algorithms such as OCRs, your embedding model, your chunk size, and so forth, so on and so forth. So let's just go back to the I don't know what I'm doing over here. So let's just go back to the initial page of Quadrant, and yeah, we have the collections. Just click on it and then go to visualize, and here you can go to this run cell and just click Command Enter or Control Enter, and you'll see this you'll see all those dots, right? So let's get a sense of them. So the core of this visualization. So actually, let me start with how these things are usually computed. So you have your embeddings, which are multidimensional vectors. In our use case, I think they have like around 1000 units. So the dimension is around 1000. The thing is that we can't visualize 1000 length vector. So usually you go to a reduction dimensional algorithm such as UMAP, which brings down all your vectors to 2 or 3 dimensions. In this case, 2. So basically we take those multidimensional vectors and project them into a 2D space to be able to visualize and get a sense of those vectors. So as you can expect, this projection is not perfect because you lose a lot of information from 1000 of dimensions to 2D, but they can get you a lot of sense on the typology, like on the geometrical structure of your vectors. So here we actually use just 3 philosophers to keep it simple. We have Turing, we have Aristotle, and we have Plato. So as you can see, here we have the Aristotle, right? You can see here on the right, the philosopher ID and name. We can see on the right that Aristotle is over here. Plato is over here, right, in this space, and we have Aristotle more scattered around here, and we also have Alan Turing over here. So we can, from a quick view, we have a understanding that our data is kind of clustered actually. So when we make a query to something about Alan Turing, we know it will be scoped to this cluster, and we know that you will retrieve something about Alan Turing. Now the question is, do we retrieve what we care about Alan Turing, right? So we can retrieve something, I don't know, we ask him about his test, the Turing test, and we retrieve something about when he was married or whatever, right? So yeah, so we'll do that a little bit further using LLM as judges. So these are more like retrieval, recall, and precision metrics that we want to answer. But the thing is that this cluster looks kind of good. Of course, it can be improved. So just to give you a sense of if we do a modification, what happens to these visualizations, I want to run a deduplication algorithm like min-max hash, right? To see that if we deduplicate, so we find similar chunks, what happens behind the scenes. So to do that, we'll actually search for module 2, where we have some, okay, so here, so we have this class under RAG, which is called long-term memory creator. And here we basically run the extraction generator, which scrapes Wikipedia and Stanford and Wikipedia and all of that to find more information about the specific philosophers. We split them into chunks. And the thing is, because per philosopher, we scrape multiple sites, there's a big chance that we might find similar information, right? So a very, I guess, naive approach to deduplicate this information is to use a technique known as a min hash, right? So yeah, the min hash algorithm, which I won't go, actually, we don't have time into going into the specifics of the algorithm, but the thing behind this is, actually, let me run the algorithm first. So let us create the long-term memory first, and while it runs, I will quickly give you more insights into this. So yeah, create long-term memory. Okay, so now it just clears the old collection and recreates it using this deduplication mechanism. So as you can see, we deduplicated for Plato 91 chunks, for Aristotle 250 chunks, and for so the thing behind this the duplication algorithm, it works kind of similar with embeddings, but we use all kinds of hashing techniques to compute a lossy vector of each chunk, with which we can find similarities between each other. So this is a lot faster than just doing string equality operations, because it works usually on a reduced number of dimensions than a whole string. And then you do something similar as similarity search. So basically you compute a vector, but instead of using embeddings, you use some hashing techniques. You reduce it like from you reduce the dimension to, let's say, 16, 52, a few 100 dimensions of each vector, and then you do something similar to semantic search to find to answer questions such as, okay, is this chunk similar to other chunks? And based on this threshold, you find the similarity. So it's really similar to semantic search, but yeah. So now let's see how this space changed. So as you can see, it haven't changed that much. Okay, So on my previous test, it did. So we can already see the non-determinism of this. Actually, let me just do something, because let me just start from scratch. So now we have a few under 1000 points because we removed some of them. So let's revisualize this. Okay, so now it was correct. So the thing is that it did not change that much, but again, if we did not have this visualization in place, we couldn't check that, right? So that's another value of having evaluation in place, but because when you do a change to your system, you can answer questions such as, okay, did it improve the system? Did it make it worse? It didn't do anything, right? So and so forth. So actually, I forgot to show you, but what it did now, as expected, it removed many points that were really overlap with each other, like this one. This here, we can see that our deduplication hasn't actually worked fine, right? Because these points actually still overlap, are really close to each other. So most probably we will need to further fine tune and tweak this algorithm or use a different algorithm. But previously we actually had many more this kind of point that were overlapping. Yeah. So yeah, so now let's move on to the next phase. So this is how we can evaluate the context within the memory. And actually, one last thing that I want to show you is how we can like zoom in into specific clusters. So as you can see here, we have this philosopher ID, philosopher name, the source where it was gathered from, a summary, and the title. So let's filter by the philosopher ID to zoom in into a specific cluster. So let's use Plato as this example. So bam, now we zoom into a specific cluster and we can see more details about Plato, right? So depending on our use case, we can further dig down and debug our vectors, our embedding space. Okay, so the next phase is to actually run some ML as judges and compute some specific metrics, because what we have done so far was more like intuitive, visual, and so on and so forth. And now we want to compute some specific metrics. This will aggregate module 2 and 3, and we will see quickly why. Okay, so okay. So before doing that, I actually forgot to do this, but I don't think it's that important, but maybe you can do it on your own if you want to. So you can further tweak with the configuration of RAG. You can tweak like the embedding model, the chunk size, especially these two, like the embedding model and the chunk size, and you can see how the vector space changes, right? So let's actually do this. Let's put the chunk size, let's increase it, let's rerun our algorithm, and while it runs, we can start moving on to the evaluation phase. So here we have two files, right? So we have the upload dataset file, which we have to implement first, which does basically it takes this file that we already prepared for you, which is called evaluation dataset, and basically we created some evaluation samples to evaluate our system on top of. So for example, we created some conversations between Sophia, this is like a random name we picked as our main character, and the philosopher itself, right? So we want for specific questions to see that it answers with the specific answers. And as you can see, we have like 3 turnarounds, and we will use the first 2. Actually, it has 4 turnarounds. So we will use the first 3 turnarounds as context, as conversational context, and we will use the last one like as the input to the system, and this one as the ground truth, like the answer ground truth to the system. So this is how the data looks like. We actually generate it using an LLM itself. So usually you want to do this by gathering data from specific use cases, from specific edge cases, especially edge cases, and develop it. As you develop the system, you want to usually grow this evaluation data set. But yeah, this is a webinar, so we did not have time to do that. But yeah, okay, so here we will start to write a little bit more code. So to keep it fast, I will just copy paste this. And because of this, let me increase the font size, okay, to see better what's going on. Because now, as I said, we'll start writing some more code. Okay, so here basically in this particular function, what we want is just take this JSON file and upload it to OPIC as an evaluation data set used to run experiments on top of. Okay, so the first thing that we want to do is, so as you can see, we load it. We load this file as a JSON, right? So we get this data path as a parameter. Next, we want to filter only for particular philosopher IDs to keep the dataset scoped to what we want. In our use case, we will use only Plato, Aristotle, and Turing. So we want to be scoped to what we want to debug. And next, we preprocess it to load from this, actually to load this dataset in a format expected by OPIC. And next, we just basically load this file to OPIC, and that's it. So here we have nothing really interesting. Okay, but where things get interesting is in this evaluate.py file. So here we actually scroll down to the end of the system and we'll build it up like this. So we have this evaluate function, which I will print it here, right? So here we need the data set that we just uploaded previously. Actually, no. So let's continue with this. So we have this data set, which we just uploaded previously. We have this evaluation task function, which is used to call our agent on every input from the data set, call our agent and get the output and the context and gather everything that we need about the agent. Here we have our actual scoring metrics, some config, and actually the use prompts, which I will show you quite soon. And actually we can see what particular prompts were used to run this experiment. So let's start with the data set, how we can get this data set. Okay. So we implemented this simple function, which basically just gets the data set based on a name. I will show it when we run this code. I will show it how it looks like, but nothing interesting so far. But now things get more interesting. So we set up an experiment config, so we actually know what we use to run this experiment. So something very simple is what model ID was used as an LLM as a judge and dataset name used to run this. And also attached to this config part of the system, we can get the used prompts, which are implemented here. And what do we do here? Oh no. Okay. And what do we do here is that we use prompt monitoring with OPIC to wrap our prompts and version them and gather them into a centralized system. I will get into the particular implementation on how we do that a little bit later, but what you have to understand here is that our prompts used in this Philo agent system known as the philosopher character card is actually tracked with OPIC as well. So we attach to this into the system and we'll know what version of the particular prompt, and we can actually visualize the prompt template itself used into the system and to run all those experiments. And now finally, we define our scoring metrics, which are as follow. So let's actually just start with the retrieval related ones, right? So we have this context recall and context precision metrics. And basically what do is they compute recall and precision between the answer and the question, right? So they will quantify questions such as, for example, the precision will quantify questions such as, is the context enough to answer that particular query, right? No, my mistake, that's recall. Is the context correct relative to the specific query? So basically, is the context relevant to that particular query? Do we have any noise in that particular query, in that particular context, or we retrieved only what we care about? And on the recall side, we answer questions such as, is the context enough relative to a specific question? Do we need more information to really answer that question fully? Okay, so let's run this experiment using just this, and then we'll move to these metrics more related to the general performance of the system. Okay, so let's go back to the README. So let's run this make upload evaluation dataset first, which will upload the dataset to OPIC. So yeah, of course that we have some bug. Let's quickly see what's going on. Dataset already exists. Okay, so this is a change done to them. Previously, it just overridden it if it already exists, but yeah, then here we go to data sets and we have this data set. Let's just delete it, okay? As they are a fast growing tool, most probably things change, right? So now let's upload it. Okay, so now it's created, it's recreated. So we go here. So here we uploaded just 12 samples to keep it simple for webinars to run in feasible timeframes. But as we can see here, we basically can look at similar things such as what we've seen in JSON, but we can see it in a similar format expected by our system. So we can just take this and throw it to the agent and other metadata used to configure the agent as expected, such as the philosopher ID. And yeah, basically we have this from these three philosophers. And then things get interesting when we, I don't know why this keeps resetting itself, but let's run the make evaluate agent, which actually runs this script, right? So as you can see, oh, we actually forgot to do one last phase. Okay, so we have to implement the evaluate task method, which actually defines that, okay, for a particular input from the data set, we pass it to this agent and we get this particular output. So because we wrote our code kind of modular, we use a philosopher factory to actually create the philosopher itself. Here, as you can see, we define per particular philosopher, we define things such as its style, its perspective, and so on and so forth. So basically we build up all the elements required in our prompt template. So we have our philosopher, and now we call the agent basically using this input messages taken from the data set, the expected output message taken from the data set. So the input messages are everything until the last turn around, and the expected output message is actually the last one. And now we call the agent using this philosopher ID. And yeah, basically that's it, I guess. So within this agent call, we call the agent not using the stream token by token method, but actually by just calling the graph once and expecting for the whole answer. So here is not streaming, it's just normal input and outputs. Okay, so now I realize that we actually don't need this piece of code. We could actually just pass the philosopher ID directly over here, but that's not that important. So we now have the response of the agent. We have the expected output message, like the ground truth of relative to this response. And we have these input messages. So the last phase is the context. Now in our use case, the context is actually the whole conversation history. So we wrote a function to just extract this conversation history from the latest state. And the latest state actually just is a instance of this, where is it? This state. So this state of the agent, where you have the context, the whole RAG context, the perspective, style, and also the whole messages, right? So we have basically everything that is going on converted to string, and we use that as the context. Okay, so now let us run this. And see what's going on. So as you can see, we have just these two metrics. Okay, okay, so we call this evaluate agent from the make file. We actually evaluated just on 6 samples to make it run faster. Okay, and meanwhile, maybe I can quickly dig into one of these metrics. So what's interesting here is that, okay, we have a particular prompt. So we call an agent with a particular prompt that is used to consider the input, output, expected output, context, and all of that, and give a score between 0 and 1. And we take the output, we parse it using a pydantic model. So we parse it into an integer, and we want to make sure that the output is in a valid format. And we pass it basically back as an integer, right? But template, so okay, so this is where we actually have the prompt template itself. We have some defined few shot templates, and here is the actual prompt itself, right? So we ask the agent to evaluate, analyze, and blah blah blah, and based on particular scenarios, just give a score, just give particular scores, right? So we have to be very careful on based on what particular scenario we want to be highly accurate, perfectly accurate, mostly accurate, and so on and so forth. So here is prompt engineering, and we really need to think deep about every word that we add, about the context, the inputs that we add, and all of that. And that's why we're leveraging already existing prompts tested by other teams is powerful. Okay, so the experiment ended. Now we can go to experiments and filter out by this our data set, which is convergence. And we can see this these experiments. So actually our latest experiment is this one. As you can see, we have just the context precision metric and the context recall metric. Based on this, we can see that our system is far from perfect, right? And if, for example, if we run another evaluation based on these metrics, let's say that we put just two samples to run it faster and to have some movement into the results, it will soon be ready, so we won't jump to another aspect. So, okay, so if we evaluate it just on two samples, okay, two samples, of course, are not enough, but I wanted to show you that you can see like the evaluation in time of these metrics. And so this is really similar to experiment trackers used to fine-tune models, because in the end, I think this is a similar iterative process, right? Where based on particular features, you want to measure them, see how they change the system and see what's going on. Okay, so if we plug in those three other metrics, basically we can just run it and it will work as before. Now, hallucination basically gives answers to questions such as, is this answer anchored into the context? So basically all the answers are related to the context, or the LLM starts to talk about something else. So it manages to quantify between 0 and 1 this particular answer question. The answer relevance answer questions more as, is the answer responding the whole question, right? And so on and so forth. Okay, and the moderation, yeah, usually looks for things such as, is the answer toxic, yes or no? Or it will be really interesting to dig into the prompts of each, but unfortunately, I don't think we have the time to do that. So as you can see, all of them are numbers between 0 and 1, and usually hallucination is good. If it's 0 is good, if it's 1 is bad. Answer relevance is the other way around. Moderation, again, 0 good, 1 bad. Context, the context metrics, 0 bad, 1 good. So yeah, the thing is that now we can start plugging in more samples and playing and measuring this and playing around with it. Okay, so now the last step that I want to show you is our prompt versioning, which is actually really simple. So intuitively, if we go here to prompt engineering prompt library, we have this convergence prompt and its version. So if you click on it, we can see basically the prompt template used to do these character impersonation things. We can see the experiments it was used in. Actually, also if we go to the experiments per se and click, let's say, on the last one, and configuration, we can see the prompt used here to run this experiment, the model ID, the dataset name, and we have a clear understanding of, okay, for the setup, for this config, we just had these results. Okay, and to do that, again, it's quite simple. It's quite simple. Okay, so it's not implemented yet. So what you've seen is from my previous test. So to do this, we just have to basically run this line of code, basically to wrap up the prompt itself into this OPIC prompt object. And I've written this wrapper class to be able to have the same interface from the prompts, regardless whether you use OPIC or just simple strings. So like this, you're not dependent on a framework, on this particular framework, or necessarily being hooked to it. So this can throw an exception and the system will still work, but you will just not measure the prompt. So let's just do a really quick change to this. I don't know, let's put a dot and let us call the agent again. And if you go now here to prompt library, we can see that now we have version 2. Okay, so we actually picked up on that change. Okay, so this is version 2, so we actually picked up on this change, right? So like this, every time you change a prompt, you can pick up on every change, and when you start measuring your experiments, you know what particular prompt version you used, so you know what prompt to actually stick to, right? Okay, so the last thing I want to show you is to close the loop and go to user feedback. This one is really tricky in a simple webinar, but I wanted to just give you a sense of it. So let's say that we are in our engineering and project management team. We want to see how our system works. And we also want to start slowly building a more robust evaluation data set. So while we monitor and we look around if this works or not and so on and so forth, we can just go to feedback scores and manually annotate basically the whole workflow. So we say that, okay, it's correct or not. We can put a quality score if we want to, then we can close this. We can go to another one. Let's assume that this is not correct and it has quality in 1 and so on and so forth. So now we can see this. And also what we can further do is just take this and add this to this data set, right? So like this, we can slowly build an evaluation data set with good and bad examples, which can also further be used for fine tuning and so on and so forth. And in the end, even if we collect this feedback in other ways than within the engineering team or internal team or QA team or whatever, we can apply the same principles from the users themselves. Okay, there things get more complicated on deciding how to get these signals, but this is not a topic for today. But the thing is that you can slowly build up your evaluation data set, a good one, a robust one with many edge cases, taking this approach. And okay, so I want to finalize this. Actually, no, I'm not done. So you can go to configuration and actually create new feedback definition and put here whatever makes sense for your use case. I manually configure this correct and quality scores, but you can do this. So go to create new feedback definition, or do exactly what I did, or do something else that makes sense for your business use case. And the last thing that I want to do is let's ask the agent a more complicated question like this one, which basically contains, what is your view on ethics when it comes to building intelligent machine? Also tell me more about the Turing task. So in theory, we might think that it needs to call the tool, the segmentation, the semantic memory twice. So let's see if it's done that. So we go to projects, convergence, let's go to the last one. So it actually did. Oh my God. So, okay, so the first call to the semantic memory is tell me more about the Turing test. And the second one is what is your view on ethics when it comes to building intelligent machines? So it actually works, right? This is the expected behavior that we want in this particular use case. So we can go to feedback scores, but correct one. And maybe depending on how the answer is, we decide on 0, 9, on 1, and so on and so forth. Okay. With that in mind, we finalized our observability workshop. I still wanted to show you many other things in this webinar, but unfortunately I don't have the time to. But what I want to highlight is that observability, evaluation, and monitoring in LLM systems and RAG systems is far from a solved solution. So you will most probably need to take what I showed you today and adapt it to a particular system, business use case, or just combine it with what you currently have, and so on and so forth. And yeah, I hope that you had the chance to learn a lot. And thank you, Comet, for inviting me here for this to host this webinar. And I hope to see you, both Comet and the audience, to my future webinars. Wish you a great day and bye.